In this lesson, we'll discuss some common shapes of quantitative data distributions and how they are related to various features we may observe in graphs or descriptive measures. A distribution refers to the way that data values are spread out or organized. In general, the shape of a distribution describes the overall appearance and may provide insight into characteristics and properties of the data. Some common shapes include skewed to the left, or negatively skewed. A data distribution that is skewed to the left will have a long left-hand tail. Most of the data will appear to the right of the distribution, with fewer data values appearing on the left. Skewed to the right, or positively skewed. A distribution that is skewed to the right has a long right-hand tail, with most of the data appearing to the left. Symmetric. A symmetric distribution has an approximately mirror image on both sides. There are two commonly observed symmetric distributions. In a uniform distribution, the frequencies of all data classes are approximately equal, so that the histogram looks relatively level. In a bell-shaped or normal distribution, the data are approximately symmetric around a mean, with the frequencies falling off on both sides of it. Many natural phenomena tend to follow a normal distribution. Another way to describe a distribution is to indicate how many peaks there are in the histogram. A distribution may be unimodal, which has one peak, or bimodal, which has two peaks. In theory, there may be more than two peaks, but when a distribution has more than two, it becomes more complex to define and interpret what exactly constitutes a peak. Based on the shape of the distribution, there are certain relationships that we can expect to see among some of the descriptive statistics we've covered. For example, if a distribution is skewed to the left, we expect for the mean to be less than the median. This is because left-skewed data will likely have some extreme values or outliers in the left tail. These outliers tend to pull the mean towards their direction. The median, however, has a property called resistance. It tends to be less affected by outliers. In a distribution that is skewed to the right, we expect for the mean to be greater than the median. For distributions that are symmetric, we expect for the mean and median to be approximately equal. Now it's important to take into account the magnitude of the data here. Consider the following two datasets. Dataset A is comprised of the values 1951, 1758, 1998, 1759, and 1334. Dataset B is comprised of the values 3.2, 3.4, 4.8, 3.8, and 8.8. The mean of dataset A is 1,760, and the median is 1,759. The mean of dataset B is 4.8, and the median is 3.8. Notice here that in both cases the mean is greater than the median by a value of 1. However, a difference of 1 in dataset A is relatively much less than a difference of 1 in dataset B, because the values in dataset A are so much larger. If a distribution is bell-shaped, or normal, not only do we expect for the mean and median to be approximately equal, but we can use the standard deviation to describe the distribution using a rule known as the empirical rule. The empirical rule states that if a distribution is normal, then approximately 68% of the data will be within one standard deviation of the mean. Approximately 95% of the data will be within two standard deviations of the mean, and all or almost all of the data will be within 3 standard deviations of the mean. For example, consider a dataset that represents the gas mileage on cars on a highway. Suppose that this distribution is approximately normal with a mean mileage of 30 miles per gallon and a standard deviation of 2 miles per gallon. We can apply the empirical rule to make the following statements about the distribution. Approximately 68% of the cars have mileage within the range of 30 minus 2 to 30 plus 2, which is about 28 to 32 miles per gallon. About 95% of the cars fall within 2 standard deviations of the mean, so the range would be 30 minus 4 to 30 plus 4, or 26 to 34 miles per gallon. Lastly, all of the cars, or almost all of the cars, will be within the range of 30 minus 6 to 30 plus 6, or 24 to 36 miles per gallon. Let's click over into R. We're going to import a dataset about Airbnb rentals in Boston. I'm going to construct a histogram of rental prices. We can see that the histogram is highly skewed to the right. Suppose now that we consider the mean and median. We find the mean to be 207.76 and the median to be 181. We see here that the mean is significantly greater than the median, which is what we expect with a right-skewed distribution. Let's look at another example. I'm going to import a dataset which includes the depth and magnitude for a series of earthquakes that occurred over a 5-year period. I'm going to call this quakes. Let's start by finding the mean and median of the depths. The mean is 8.197087, and the median is 8.211. Because these quantities are pretty close, we expect the distribution of depths to be symmetric. Let's take a look at the histogram. From the histogram, it appears that the distribution is symmetric. It also appears to be approximately normal. Because the distribution is approximately normal, we can describe it further using the empirical rule. We start by finding the standard deviation. The standard deviation is computed as 3.192226. I'm going to assign the mean to a variable called m and the standard deviation to a variable called s. Now, we know that the empirical rule tells us that approximately 68% of the earthquake depths should fall within 1 standard deviation of the mean. So we find that approximately 68% of depths are between 5.004861 and 11.38931. We also know that approximately 95% of the depths in the study should fall within 2 standard deviations of the mean. So approximately 95% are between 1.812635 and 14.58154. Lastly, we find that all or almost all of the depths will be between negative 1.37951 and 17.77376. Let's talk for a moment about a related topic to the empirical rule, which is z-scores. Simply put, a z-score indicates how many standard deviations away a data point is from the mean. Given a data value x from a distribution with a given mean and standard deviation, the z-score of x is z equals x minus the mean divided by the standard deviation. For example, we know that the earthquake depths have a mean of approximately mu equals 8.1971 and standard deviation of sigma equals 3.1922. Let's take a look at the 6th earthquake in our list. I'm going to call this depth x. We see that the 6th earthquake has a depth of 10.445. Obviously, this value is greater than the mean, but by how much? Well, one way to answer this is with a z-score. We find the z-score to be approximately 0.7042, which isn't all that much. Think about what the empirical rule tells us. About 95% of the data fall within 2 standard deviations of the mean. That is, the majority of the data have z-scores between -2 and 2. So a z-score of 0.7042 is well within what we'd expect. The 117th earthquake in our list has a depth of 18.192. Let's find the z-score of this depth. We find that this earthquake has a z-score of 3.1310. Is a depth of 18.192 an unusual value? Well, I would say so. From the empirical rule, we know that almost all of the data is within 3 standard deviations of the mean. So a z-score of 3.1310 is kind of off the charts. Okay, I'm going to take us in a little different direction now. Suppose that we wanted to explore the data based on whether the earthquake is likely to cause damage, which happens with a magnitude of 5.0 or higher, or is not likely to cause damage, which happens when the magnitude is less than 5.0. We will now use R to filter the datasets. The first thing we need to do is install a package that makes data manipulation easier in R. The install packages dplyr command only needs to be run once. I'm not going to run it here because it's already installed on my computer. Once the package is installed, we will call up the library using the library dplyr command. Part of this package is a command called filter. The filter command allows us to create a new data set from an existing one based on a given condition. Let's create a new data set that only consists of earthquakes with a magnitude that is less than 5.0. I'll call this new data set minor quakes. I use the filter command, pulling from the big data set quakes, with the condition that the variable magnitude is less than 5.0. Once we've run this command, let's take a look at minor quakes. As we can see, minor quakes is comprised of only earthquakes with a magnitude less than 5.0. Now similarly, I'll create a data set called major quakes that is comprised of only those with a magnitude of 5.0 or greater. Now suppose that we want to know whether the depths are significantly different between minor and major earthquakes. Let's find the mean of the depths for both minor and major earthquakes. The mean of the minor earthquake depths is 8.197305, while the mean of major earthquake depths is 8.076548. At first glance, it doesn't appear that there is a large difference between the mean depths. By looking at the histograms of both minor and major earthquakes, it also appears that the distribution of the depths are pretty similar to each other. Overall, it doesn't appear that the magnitude of the earthquake is much affected by the depth. Okay, so in this module we explored various data distributions, from skewed to symmetric patterns and their real-world implications. We also touched on the empirical rule and applied our understanding using R. Best of luck as you move on to the next lesson.